What if I told you that right now, at this very moment, you are hurtling through space at over 100,000 kilometers per hour? You don't feel it, but our planet is racing around a giant nuclear explosion that has been burning for 5 billion years. And here's the crazy part. That explosion, our sun, is actually the safest place for us in a universe that is actively trying to destroy everything in it. From planets that rain diamonds to moons hiding oceans beneath frozen shells, from black holes that swallow entire stars to invisible forces stretching the fabric of reality itself, the cosmos is a place of unimaginable beauty and terrifying danger. Today, we're going on a journey from the heart of our sun to the very edge of the observable universe, and along the way, you're going to discover why you shouldn't exist, how you're made of dead stars, and what the future holds for everything that ever was or ever will be. Buckle up, because the universe is way stranger than you ever imagined. The star that keeps us alive. Let's start with something you see every single day but probably never think about in the right way. The sun. It looks like a peaceful yellow ball hanging in the sky, but that's one of the biggest lies your eyes have ever told you. The sun is actually a raging monster of nuclear fury, a sphere of plasma so hot and so violent that nothing on Earth can even come close to recreating what happens in its core. Deep inside the sun, at its very center, the temperature reaches 15 million degrees Celsius. That's not a typo. 15 million. At those temperatures and pressures, something remarkable happens that seems almost like magic, but is actually pure physics. Hydrogen atoms are being smashed together so hard that they fuse into helium, and when they do, a tiny bit of matter disappears. That missing matter gets converted directly into energy, according to Einstein's famous equation. Every single second, the sun loses 4 million tons of its own mass and converts it into the light and heat that makes life on Earth possible. Think about that for a moment. The warmth on your face on a sunny day, the energy that makes plants grow, the fossil fuels we burn, the food you eat, all of it, every single bit of it, comes from matter being destroyed at the center of a star. You are literally living off nuclear fusion happening 93 million miles away. But here's where it gets really wild. That energy being created in the core right now won't reach the surface of the sun for another 100,000 years. The sun is so dense, so packed with matter, that photons of light bounce around inside it like a pinball in an arcade machine, slowly working their way outward over millennia. Then, once they finally break free from the surface, they race across the vacuum of space and hit your skin just 8 minutes and 20 seconds later. The sun isn't smooth and calm on the outside either. Its surface, called the photosphere, is a churning mess of granules, each one the size of a country, where hot gas rises from below, cools off, and sinks back down again. It's like watching a pot of boiling water, except this pot is 1,000,000 times bigger than Earth and hot enough to vaporize any known substance. And then there are the sunspots, those dark patches that appear and disappear over an 11-year cycle. They look dark only because they're slightly cooler than their surroundings, but don't let that fool you. A sunspot is still around 4,000 degrees Celsius, hot enough to melt just about anything. These spots are created by the sun's magnetic field getting all twisted and tangled, preventing hot gas from rising to the surface in those areas. But the real fireworks happen above the surface, in the sun's atmosphere. Sometimes, the twisted magnetic field lines snap like overstretched rubber bands, and when they do, they release flares of energy that dwarf anything we can produce on Earth. A single solar flare can release the energy equivalent of 1 billion megatons of TNT. That's more than every nuclear weapon ever built, detonated all at once. These flares blast out streams of charged particles that race across the solar system. And when they hit Earth, they create the beautiful dancing lights we call auroras, the northern and southern lights. The sun is the reason we exist, but it also has an expiration date. In about 5 billion years, it will run out of hydrogen fuel in its core. When that happens, the delicate balance between the outward push of radiation and the inward pull of gravity will collapse. The sun will swell up into a red giant, growing so large that it will swallow Mercury, then Venus, and come dangerously close to Earth. Our planet will become a scorched, lifeless rock, its oceans boiled away into space, its surface melted into slag. Eventually, the sun will shed its outer layers into space, creating a beautiful glowing nebula, while its core collapses into a white dwarf, a dense stellar corpse about the size of Earth. That white dwarf will slowly cool over trillions of years until it becomes a cold, dark black dwarf, and our solar system will be a frozen graveyard. But don't worry about packing your bags just yet. We've got a few billion years to figure something out. The Scorched Messenger. Now let's leave the sun and visit the planet closest to it. Mercury is a world of extremes, a tiny scarred rock racing around our star faster than any other planet. It completes an orbit in just 88 Earth days, which is how it got its name after the swift messenger god of Roman mythology. Mercury is a weird place, and I mean genuinely weird in ways that mess with your sense of how planets should work. For starters, its day is twice as long as its year. Let me explain that because it sounds impossible. Mercury rotates on its axis so slowly that it takes 176 Earth days for the sun to rise, cross the sky, and set again. But it only takes 88 days to orbit the sun completely. So if you were standing on Mercury, you'd experience 2 years for every single day. Happy birthday twice before lunch tomorrow. The temperatures on Mercury are absolutely brutal. During the day, the surface can reach 450 degrees Celsius, hot enough to melt lead. But at night, without any atmosphere to trap heat, temperatures plummet to minus 180 degrees Celsius. That's a temperature swing of over 600 degrees, the most extreme of any planet in our solar system. No other world goes from oven to freezer quite like Mercury does. Mercury's surface is covered in craters, looking almost identical to our moon. That's because both worlds lack atmospheres and geological activity to erase the scars of ancient impacts. Every crater on Mercury tells a story of the violent early days of our solar system, when rocks and debris were flying everywhere, smashing into everything. One impact was so massive that it created the Caloris Basin, a crater spanning over 1,300 kilometers. The force of that impact was so powerful that it sent shockwaves all the way through the planet and created chaotic terrain on the exact opposite side of Mercury. Here's something that will blow your mind. Despite being the closest planet to the Sun, Mercury isn't the hottest planet. That honor goes to Venus. And speaking of Venus, we should probably talk about how a planet that might have once been Earth's twin became a nightmarish hellscape. The evil twin. Venus is almost exactly the same size as Earth. It has a similar mass, a similar composition, and it formed from the same cloud of gas and dust at roughly the same distance from the Sun. In the early days of the solar system, Venus might have had oceans of liquid water, a thick but breathable atmosphere, and perhaps even the conditions necessary for life to begin. It could have been a paradise. But something went horribly, catastrophically wrong. Today, Venus is the most hostile environment in the inner solar system. Its atmosphere is 90 times denser than Earth's, composed almost entirely of carbon dioxide with clouds of sulfuric acid drifting through the sky. The pressure at the surface is equivalent to being a kilometer deep in Earth's ocean. You would be simultaneously crushed, suffocated, corroded, and cooked. And cooked you would be. Venus has a surface temperature of 475 degrees Celsius, hot enough to melt lead, tin, and zinc. It's hotter than Mercury, even though it's nearly twice as far from the sun. The reason is the most extreme greenhouse effect in the solar system. The thick carbon dioxide atmosphere traps heat like a blanket, allowing sunlight in but preventing infrared radiation from escaping back into space. Once Venus started heating up, it couldn't stop. Scientists believe this runaway greenhouse effect might have been triggered billions of years ago when the young sun grew slightly brighter and warmer. Venus was on the inner edge of what we call the habitable zone, the region around a star where liquid water can exist. As the sun's output increased, Venus's oceans began to evaporate. Water vapor is also a greenhouse gas, so this added even more heat. More heat meant more evaporation, which meant more heat, in a vicious cycle that boiled the oceans away completely. The hydrogen from the water molecules was lost to space, stripped away by the solar wind, while the oxygen probably combined with carbon to form the thick carbon dioxide atmosphere we see today. Venus is a warning. It shows us what can happen to a planet when its climate tips past the point of no return. Earth has been slowly warming due to our own greenhouse gas emissions. And while we're nowhere near the conditions that destroyed Venus, the physics is the same. Carbon dioxide traps heat. More carbon dioxide means more heat. It's not magic. It's just how molecules interact with light. The Soviet Union actually landed several spacecraft on Venus in the 1970s and 1980s. The probes managed to transmit images of a barren, rocky surface lit by an eerie orange glow before the heat and pressure destroyed them within minutes. Those images are the only photographs ever taken from the surface of another planet besides Mars, and they show a world that is utterly alien and utterly dead. Volcanoes once covered Venus with lava, and there's evidence that volcanic activity might still be occurring today. The planet's surface is geologically young, perhaps only 500 million years old on average, suggesting that Venus periodically resurfaces itself through massive volcanic eruptions. Imagine the entire surface of a planet being recycled by lava flows. That's Venus. The pale blue dot. Now we come home, to the only place in the known universe where life definitely exists, Earth. Our planet is a cosmic miracle, a precious oasis of water and oxygen floating in an endless void of radiation and vacuum. From space, Earth looks like a beautiful blue marble, with swirling white clouds, green and brown land masses, and those gorgeous blue oceans that cover more than 2/3 of the surface. Those oceans are the key to everything. Water is the universal solvent, the medium in which the chemistry of life can take place. Without liquid water, life as we know it simply cannot exist. But Earth wasn't always the habitable paradise it is today. 4.5 billion years ago, our planet was a molten hellscape, constantly bombarded by asteroids and comets, with no solid surface to speak of. Slowly, over hundreds of millions of years, the surface cooled enough to form a crust, and water vapor released by volcanic eruptions condensed into the first oceans. Life appeared remarkably quickly after that, geologically speaking. The oldest fossils we found are around 3.8 billion years old, meaning life got started within a few 100 million years of the planet becoming habitable. At first, it was just simple single-celled organisms, bacteria-like creatures that lived in the oceans and around volcanic vents. For over 2 billion years, that's all there was. Just microbes. No plants, no animals, no fish, no dinosaurs. Just tiny cells drifting in ancient seas. Then something incredible happened. Some of those microbes evolved the ability to photosynthesize, to capture sunlight, and use it to convert carbon dioxide and water into sugar and oxygen. This was a revolutionary innovation, and it slowly transformed the entire planet. Oxygen began to accumulate in the atmosphere, eventually reaching levels high enough to support complex life. An ozone layer formed, protecting the surface from harmful ultraviolet radiation. The stage was set for the explosion of life that would follow. About 540 million years ago, life suddenly diversified in what scientists call the Cambrian explosion. Within a relatively short period, all the major body plans we see in animals today appeared for the first time. Eyes evolved, shells evolved. Predators and prey began their eternal dance. Life left the oceans and colonized the land, first plants, then insects, then vertebrates. Earth's surface is constantly changing, shaped by forces from deep within the planet. The crust is divided into massive tectonic plates that slowly drift on top of the mantle beneath. Where plates collide, mountains rise and earthquakes shake the ground. Where they pull apart, new crust forms from magma welling up from below. Where one plate slides beneath another, volcanoes erupt and deep trenches form in the ocean floor. This plate tectonics is actually crucial for life. It recycles carbon dioxide from the atmosphere back into rocks and then releases it again through volcanoes, maintaining a stable climate over billions of years. It creates diverse habitats, from mountain ranges to ocean basins. Mars doesn't have active plate tectonics anymore, and Venus may have lost its water partly because it lacks this geological thermostat. The tilt of Earth's axis gives us our seasons, as first one hemisphere and then the other leans toward the sun over the course of a year. The rotation of the planet gives us day and night. The magnetic field generated by our liquid iron core shields us from the solar wind and cosmic radiation. Everything about our planet seems precisely tuned to support life. And while that might sound like design, it's actually just the result of being the one planet in trillions where everything happened to work out. Our faithful companion. Look up on a clear night and you'll see our moon, the only natural satellite of Earth, and the only other world humans have ever walked upon. The moon has been our constant companion for almost the entire history of our planet, and its presence has shaped Earth in ways you might not expect. The leading theory for how the moon formed is genuinely dramatic. About 50 million years after Earth itself coalesced from the solar nebula, a Mars-sized object, sometimes called Theia, crashed into our young planet in a glancing blow. The impact was so violent that it melted both bodies, spraying a vast cloud of molten rock into orbit around Earth. Within just a year or two, this debris clumped together to form the moon, initially orbiting much closer to Earth than it does today. This impact origin explains a lot about the moon. It explains why the moon has no iron core of its own, since the iron from both Earth and Theia sank to the center of Earth during the collision. It explains why the moon's composition is so similar to Earth's mantle, and it explains why the moon is so unusually large compared to its planet. Most moons are tiny compared to what they orbit, but ours is a full quarter of Earth's diameter. In those early days, the moon was perhaps 20 times closer than it is now, and both bodies were still glowing from the heat of formation. The gravitational tug between them was immense, creating tidal bulges in the molten rock of both worlds. Over billions of years, this tidal interaction has been transferring energy from Earth's rotation to the moon's orbit. Earth's days have been getting longer, and the moon has been drifting farther away. We can actually measure this drift using laser reflectors left on the moon by Apollo astronauts. Scientists bounce laser beams off these reflectors and time how long it takes for the light to return. The measurements show that the moon is receding from Earth at about 3.8 centimeters per year. That doesn't sound like much, but over hundreds of millions of years, it adds up. The moon stabilizes Earth's axial tilt, keeping it at a relatively constant 23 degrees. Without the moon, Earth would wobble chaotically, with the axial tilt varying wildly over millions of years. This would cause extreme climate swings that might have prevented complex life from evolving. So in a very real sense, we might owe our existence to that ancient collision that created our faithful companion. The moon's gravitational pull also causes the ocean tides. As the moon orbits Earth, it creates a bulge of water on the side of Earth facing it, and another bulge on the opposite side. As Earth rotates beneath these bulges, coastlines experience high and low tides roughly twice a day. Some scientists believe these tides might have been important for the origin of life, creating pools where complex chemistry could occur in a cycle of wetting and drying. When you look at the moon, you're seeing a world frozen in time. Without an atmosphere or active geology, nothing erases the ancient impact craters that cover its surface. The dark patches you can see with the naked eye are called maria, Latin for seas, though they contain no water. They are actually vast plains of ancient lava that flooded the floor of enormous impact basins billions of years ago. The lighter regions are the heavily cratered highlands, the original ancient crust of the moon.
The Red Planet.
Mars has captured human imagination for centuries. It's the planet most like Earth, with polar ice caps, seasons, and a day only slightly longer than our own. For a long time, people even believed there might be intelligent life there, building canals to transport water across the desert surface. That turned out to be an optical illusion and wishful thinking. But the dream of Mars has never died. Today, we know Mars is a cold, dry desert with an atmosphere so thin that you couldn't survive on the surface for more than a few seconds without a spacesuit. The air pressure is less than 1% of Earth's, so thin that any exposed liquid water would boil away almost instantly, even though the temperature is well below freezing. It's a world of rust-colored rocks and dusty plains swept by planet-wide dust storms that can obscure the entire surface for months. But Mars wasn't always this way. Evidence collected by rovers and orbiters over the past few decades tells a different story. Billions of years ago, Mars was warmer and wetter. Rivers carved channels into its surface. Lakes filled craters. There might even have been a vast ocean covering much of the northern hemisphere. The conditions for life might have existed on ancient Mars, and the possibility that microbial life once evolved there, or might still survive deep underground, drives much of our exploration today. What happened to Mars? Why did it lose its water and become the frozen desert we see today? The answer lies in the planet's size. Mars is smaller than Earth, with only about 1/10 of our planet's mass. Its core cooled faster, its magnetic field died, and without that protective magnetic shield, The solar wind was able to strip away the atmosphere molecule by molecule over billions of years. As the atmosphere thinned, the greenhouse effect weakened and Mars froze. Mars is home to the largest volcano in the solar system, Olympus Mons. This shield volcano rises over 20 kilometers above the surrounding plains, 3 times higher than Mount Everest. Its base is so wide that you could fit the entire state of Arizona inside it. On Earth, volcanoes this large can't exist because tectonic plates move, carrying the volcano away from the hot spot that feeds it. But Mars has no plate tectonics, so Olympus Mons was able to build up over billions of years as lava piled on top of lava. Mars also has the largest canyon in the solar system, Valles Marineris. This system of gorges stretches over 4,000 kilometers, roughly the distance from New York to Los Angeles. It's up to 7 kilometers deep in places, dwarfing the Grand Canyon. Scientists believe it formed as the Tharsis Bulge, a massive volcanic plateau, rose and cracked the crust. We've sent more spacecraft to Mars than to any other planet. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have rolled across its surface, analyzing rocks and searching for signs of past life. Perseverance is even collecting samples that will eventually be returned to Earth by a future mission, allowing scientists to study Martian rocks in laboratories for the first time. Mars is the most likely destination for human explorers beyond the Moon. The challenges are immense, including radiation exposure during the journey, the difficulty of landing heavy payloads, and the need to produce water, oxygen, and fuel from local resources. But many people believe that within this century, humans will set foot on Mars and begin the transformation of our species from inhabitants of one world to citizens of two. The Cosmic Shooting Gallery. Between Mars and Jupiter lies a region of space that tells the story of a planet that never was. The asteroid belt is home to millions of rocky and metallic objects, ranging from tiny pebbles to the dwarf planet Ceres, which is nearly 1,000 kilometers across. For a long time, people thought the asteroid belt was the remains of a planet that exploded or was destroyed. The truth is more subtle. Jupiter's gravity prevented these objects from ever coming together in the first place. When the solar system was forming, Jupiter grew large and massive very quickly, and its gravitational influence created a region where planetesimals, the building blocks of planets, could never peacefully accumulate. They would collide, sure, but the gravitational perturbations from Jupiter kept them stirred up, preventing them from merging into a larger body. The asteroid belt is not debris from destruction. It's cosmic rubble that never got the chance to become something more. Most asteroids in the main belt are no threat to Earth. Their orbits are stable and far from us. But there's another population of asteroids that should keep you awake at night if you think about it too hard. Near-Earth asteroids are objects whose orbits bring them close to our planet. Many of them are entirely harmless, passing millions of kilometers away. But some cross Earth's orbit in ways that create the possibility of collision. 66 million years ago, an asteroid about 10 kilometers across slammed into what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to billions of nuclear bombs, creating a crater almost 200 kilometers across. The effects were apocalyptic. Wildfires swept across continents. A cloud of debris blocked out the sun for months or years, collapsing food chains. 3/4 of all species on Earth went extinct. including all the non-bird dinosaurs that had dominated the planet for over 100 million years. This was not a freak event. Impacts like this have happened multiple times throughout Earth's history, and they will happen again. The only question is, when? That's why astronomers around the world are working to find and track every near-Earth asteroid large enough to cause significant damage. The good news is that we've found most of the truly large ones, the planet killers, and none of them are on collision courses with Earth anytime soon. The bad news is that smaller asteroids, ones that could still devastate a city or region, are much harder to spot. If we do find an asteroid heading our way, we might be able to do something about it, but only if we have enough warning time. Scientists have proposed various deflection methods, from gently nudging the asteroid with a spacecraft that pushes against it for years, to using a nuclear explosion to vaporize part of its surface and push it off course with the recoil. In 2022, NASA's DART mission successfully demonstrated the first method by crashing into a small asteroid moon and measurably changing its orbit. For the first time in history, humans have proven we can alter the trajectory of a celestial body. It's our first real planetary defense test, and it worked. The King of Planets. Now we leave the inner solar system and venture into the realm of the gas giants, and the first one we encounter is a monster. Jupiter is the largest planet in our solar system, more massive than all the other planets combined. If you gathered up all the material in every other planet, moon, asteroid, and comet, you'd still have less mass than Jupiter. It's a world so vast that over 1,300 Earths could fit inside it. Jupiter is not a rocky planet like Earth or Mars. It has no solid surface you could land on. Instead, it's a deep, deep atmosphere of hydrogen and helium that gradually becomes denser and hotter as you descend toward the center. If you tried to fly a spacecraft into Jupiter, you'd first encounter the cloud tops, moving at wind speeds of hundreds of kilometers per hour. As you dropped lower, the pressure would increase, the temperature would rise, and eventually the hydrogen gas would become so compressed that it would behave like a liquid. Deeper still, under pressures millions of times greater than Earth's atmosphere, the hydrogen would become metallic, conducting electricity like a metal. At the very center of Jupiter, there may be a rocky core several times the mass of Earth, but we're not entirely sure. The temperatures and pressures there are so extreme that the material doesn't behave like anything we're familiar with. The core might be 15 times hotter than the surface of the Sun. Jupiter's most famous feature is the Great Red Spot, a storm that has been raging for at least 300 years and possibly much longer. This anticyclone is larger than Earth itself, a swirling vortex of wind and cloud that somehow maintains itself century after century. We don't fully understand why it persists or what powers it. Other storms on Jupiter come and go, but the Great Red Spot endures. The planet rotates incredibly fast, completing a full turn in just under 10 hours. This rapid rotation creates the alternating bands of light and dark clouds we see in images, zones, and belts, where atmospheric currents flow in opposite directions. It also causes the planet to bulge at the equator, making Jupiter noticeably fatter around the middle than from pole to pole. Jupiter has a powerful magnetic field, the strongest of any planet in the solar system. This field is generated by currents in the metallic hydrogen layer deep inside, and it traps intense belts of radiation around the planet. These radiation belts are so powerful that they would kill an unprotected human in minutes. Any future exploration of Jupiter's moons will have to account for this hazardous environment. Speaking of moons, Jupiter has at least 95 of them, and more are being discovered all the time. Most are small, irregular, captured asteroids, but 4 of them are large enough to be considered worlds in their own right. These are the Galilean moons, named after Galileo, who first observed them through his primitive telescope over 400 years ago. Their names are Io, Europa, Ganymede, and Callisto, and each one is stranger than the last. Io is the most volcanically active body in the solar system. Its surface is covered with erupting volcanoes that constantly resurface the moon, which is why it has no impact craters. The volcanic activity is driven by tidal heating, the flexing of Io's interior as it's pulled back and forth by Jupiter's gravity and the gravity of the other large moons. This flexing generates heat in the same way that bending a paperclip back and forth makes it warm. On Io, this effect is so extreme that the interior is partially molten, and sulfurous lava regularly erupts onto the surface. Europa is perhaps the most intriguing moon in the entire solar system. Its surface is covered with smooth, fractured water ice, crisscrossed with reddish-brown lines and ridges. Below that ice shell, scientists believe there is a global ocean of liquid water, kept warm by tidal heating similar to what drives Io's volcanoes. This ocean might contain more than twice as much water as all of Earth's oceans combined. And where there is liquid water and energy, there might be life. Europa is one of the prime targets in our search for life beyond Earth, and future missions will try to peer through or even drill through the ice to explore what lies beneath. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It has its own magnetic field, the only moon known to have one. Ganymede also likely has a subsurface ocean, though deeper and perhaps less accessible than Europa's. Callisto is similar in size, heavily cratered and ancient. It too may have a subsurface ocean, making the Jupiter system potentially rich in habitable environments. Lord of the Rings. Beyond Jupiter, almost twice as far from the Sun, lies the most beautiful planet in the solar system. Saturn is famous for its magnificent ring system, a broad, flat disk of ice and rock that extends hundreds of thousands of kilometers from the planet, but is only about a kilometer thick. Through a telescope, Saturn looks like nothing else, a golden globe encircled by ghostly halos. It's been capturing imaginations since Galileo first glimpsed it and couldn't figure out what he was seeing. Saturn is the second largest planet, a gas giant similar in composition to Jupiter, but significantly less massive. It's so light and fluffy, in fact, that its average density is less than that of water. If you could find a bathtub big enough, Saturn would float. This low density is because Saturn is made mostly of hydrogen and helium, with a smaller rocky core than Jupiter. The rings are made of countless particles, from tiny grains of ice to chunks the size of houses, all orbiting Saturn like a swarm of tiny moons. Nobody is entirely sure how the rings formed. They might be the debris of a moon that strayed too close to Saturn and was torn apart by tidal forces. They might be material left over from Saturn's formation that never coalesced into a moon. Or they might be the remains of a collision between moons. What we do know is that the rings are surprisingly young, perhaps only 100 million years old, which means they're a temporary feature of the solar system. Eventually, they'll be gone, the particles either falling into Saturn or drifting away into space. Saturn has over 100 moons, and the most remarkable by far is Titan. Titan is the second largest moon in the solar system, bigger than Mercury, and it's the only moon with a thick atmosphere. That atmosphere is mostly nitrogen, like Earth's, but mixed with methane and other hydrocarbons that form a dense orange haze. The surface pressure is actually higher than Earth's sea level pressure. On Titan's surface, there are lakes and seas, rivers and rain. But this isn't a water cycle. It's a methane cycle. The temperature on Titan is around minus 170 degrees Celsius, so cold that water ice is hard as rock, and methane exists as a liquid. Methane rain falls from methane clouds into methane lakes that reflect the pale light of the distant sun. It's an alien world unlike anything else we know. Scientists speculate about whether life could exist on Titan, but it would have to be radically different from life on Earth. Instead of water, it would use liquid methane or ethane as a solvent. The chemistry would be utterly foreign. It's a long shot, but Titan represents a different kind of habitable environment, one that challenges our assumptions about what life needs. The ice giants. Beyond Saturn, the solar system becomes colder, darker, and stranger. Uranus and Neptune are often called ice giants to distinguish them from the gas giants Jupiter and Saturn. They're smaller, denser, and composed largely of water, ammonia, and methane ices rather than hydrogen and helium. Uranus is peculiar in many ways. Its axis of rotation is tilted over 90 degrees, meaning it essentially rolls around the sun on its side. Scientists believe a massive collision early in its history knocked Uranus onto its side. This extreme tilt means that Uranus experiences the most bizarre seasons of any planet. During its 84-year orbit, each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness. Uranus is the coldest planet in the solar system, even colder than Neptune despite being closer to the Sun. This is because Uranus, unlike most planets, doesn't seem to emit much internal heat. Its deep interior is surprisingly calm and cold for reasons scientists don't fully understand. The atmosphere is a bland, featureless blue-green, colored by methane that absorbs red light. Neptune is similar in size to Uranus, but more active and energetic. It has the fastest winds in the solar system, blowing at speeds exceeding 2,000 kilometers per hour. Storms rage across its deep blue surface, sometimes lasting for years before fading away. Neptune also has a faint ring system and over a dozen moons. The largest of Neptune's moons is Triton, a world almost certainly captured from the Kuiper Belt billions of years ago. Triton orbits Neptune backward, in the opposite direction of the planet's rotation, and it's slowly spiraling inward. In a few billion years, it will cross the Roche limit, the point where tidal forces will tear it apart, and Neptune might gain a ring system rivaling Saturn's. Triton is one of the coldest objects in the solar system, with surface temperatures around minus 235 degrees Celsius. Despite this extreme cold, Voyager 2 observed geysers erupting from its surface, shooting dark material several kilometers into the thin atmosphere. This activity is powered by the weak sunlight warming nitrogen ice, which sublimates and erupts through the surface. Even at the edge of the solar system, worlds are dynamic and surprising. The edge of sunlight. Beyond Neptune lies the Kuiper Belt, a vast region populated by icy bodies left over from the formation of the solar system. The most famous resident of the Kuiper Belt is Pluto, once considered the 9th planet before being reclassified as a dwarf planet in 2006. This reclassification was controversial, but it reflects our improving understanding of the solar system's architecture. Pluto is a small, icy world about 2/3 the diameter of our moon. Its orbit is highly elliptical, sometimes bringing it closer to the Sun than Neptune, and sometimes taking it nearly 8 billion kilometers away. At that distance, the Sun appears as nothing more than a very bright star, and the temperature hovers around minus 230 degrees Celsius. Despite its small size and distant location, Pluto turned out to be remarkably complex when NASA's New Horizons spacecraft flew by in 2015. The images revealed mountains of water ice, towering 3 kilometers high, vast nitrogen ice plains that appear to flow like glaciers, and a thin haze of nitrogen and methane in the atmosphere. Pluto has seasons, weather, and active geology. It's a dynamic world at the frozen edge of the solar system. Pluto has 5 known moons, the largest of which is Charon. Charon is so large relative to Pluto that the two bodies orbit a common center of gravity located in the space between them. Some scientists consider them a binary dwarf planet system, rather than a planet with a moon. Charon itself has canyons, mountains, and a curious dark red cap at its north pole made of organic compounds. Beyond Pluto, the Kuiper Belt extends for billions of kilometers, populated by thousands of known objects, and likely millions yet to be discovered. Some of these Kuiper Belt objects are almost as large as Pluto, and might someday be classified as dwarf planets themselves. This region is the source of short-period comets, icy bodies that occasionally get perturbed onto orbits that bring them into the inner solar system. Even farther out, at the very edge of the Sun's gravitational influence, lies the Oort cloud, a theoretical shell of icy objects surrounding the solar system at distances up to a light-year away. The Oort cloud has never been directly observed, but its existence is inferred from the orbits of long-period comets. These comets take thousands or millions of years to complete one orbit, diving into the inner solar system from random directions before swinging back out into the deep freeze. The Oort cloud marks the boundary where our Sun's gravity weakens to the point where passing stars can perturb objects. It's the true edge of our solar system, where the Sun's influence finally gives way to the vast spaces between stars. Visitors from the deep. Comets are time capsules from the birth of the solar system. These icy bodies, composed of frozen water, carbon dioxide, methane, and ammonia mixed with dust and rock, have remained largely unchanged for 4.5 billion years. When a comet falls toward the inner solar system, the Sun's heat begins to vaporize its ices, releasing gas and dust that form the characteristic tail. Actually, comets have 2 tails. The ion tail, or gas tail, is made of charged particles pushed directly away from the Sun by the solar wind. It glows blue from ionized carbon monoxide and always points straight away from the Sun, regardless of which direction the comet is moving. The dust tail is made of heavier particles released as the ice sublimates. These particles are pushed more gently by the pressure of sunlight, forming a broader, curved tail that follows the comet's orbit. The most famous comet is Halley's Comet, which returns to the inner solar system roughly every 76 years. It has been observed and recorded for millennia. The Bayeux Tapestry, depicting the Norman invasion of England in 1066, shows Halley's Comet as an omen. Some scholars have even suggested that the Star of Bethlehem might have been a comet, though this is speculative. Comets may have played a crucial role in Earth's early history. They contained significant amounts of water ice and organic molecules. During the period of heavy bombardment billions of years ago, comets raining down on Earth could have delivered much of the water that fills our oceans today. They might also have seeded our planet with the complex organic molecules that are the precursors to life. In a very real sense, we might all be descended from comets. When Earth passes through the trail of debris left by a comet, we experience meteor showers. The dust particles, some smaller than grains of sand, hit our atmosphere at tens of kilometers per second and burn up from friction, creating the streaks of light we call meteors or shooting stars. These showers occur at the same time each year as Earth crosses the same regions of cometary debris. The Perseids in August and the Geminids in December are among the most reliable and spectacular annual meteor showers. Occasionally, a larger piece of space rock survives its fiery passage through the atmosphere and lands on the ground. These are meteorites, and they provide scientists with samples of material from asteroids, the Moon, Mars, and even the early solar system. Some meteorites contain minerals that could only have formed before the sun existed. Grains of stardust from ancient supernova explosions preserved for billions of years in space. The star-spangled sky. When you look up at the night sky, you're seeing light that has traveled immense distances to reach your eyes. Even the nearest star beyond the sun, Proxima Centauri, is over 4 light-years away, meaning the light you see left that star more than 4 years ago. Many of the stars visible to the naked eye are hundreds of light-years distant, and the farthest objects you can see, the Andromeda Galaxy on a clear, dark night, is over 2 million light-years away. The stars appear to be fixed in patterns we call constellations. These patterns have been recognized and named by cultures around the world for thousands of years. The Greeks saw heroes and monsters in the stars, telling stories of Orion the hunter, Ursa Major the great bear, and the winged horse Pegasus. Other cultures had their own interpretations, seeing different figures in the same arrangements of stars. Constellations are useful for navigation and as a way to organize the sky, but they're also an illusion. The stars in a constellation aren't actually related to each other. They just happen to be roughly in the same direction as seen from Earth. The stars of Orion, for example, range from about 250 to over 2,000 light-years away. If you could view Orion from a different angle, the familiar pattern would dissolve into random points of light. Stars come in a wide range of sizes, temperatures, and colors. The hottest stars are blue, with surface temperatures exceeding 20,000 degrees Celsius. Cooler stars are yellow, orange, or red. Our Sun is a yellow star with a surface temperature of about 5,500 degrees Celsius, making it a fairly average specimen. The color of a star tells you about its temperature, but not its size. There are blue giant stars and red giant stars. There are also tiny dense stars called white dwarfs, and even tinier neutron stars. The range of stellar sizes is staggering. The largest known stars, red supergiants like Betelgeuse in Orion, are so vast that if you placed one at the center of our solar system, its surface would extend beyond the orbit of Jupiter. These stars are millions of times the volume of our Sun. Stars are born in nebulae, vast clouds of gas and dust that collapse under their own gravity. As a clump of gas collapses, it heats up and eventually ignites nuclear fusion in its core, becoming a new star. The leftovers form a disk around the star, and planets can condense from this disk. We've now found thousands of planets around other stars, and the evidence suggests that planets are common in the galaxy. The violent deaths of stars. Stars don't live forever. They burn through their fuel, change, and eventually die. The way a star dies depends almost entirely on its mass. Stars like our Sun have relatively peaceful deaths. After about 10 billion years on the main sequence, a Sun-like star exhausts the hydrogen in its core and begins to change. The core contracts and heats up while the outer layers expand and cool, transforming the star into a red giant. Our Sun will eventually swell to perhaps 100 times its current size, engulfing the inner planets. After the red giant phase, the star sheds its outer layers into space, creating a beautiful expanding shell of gas called a planetary nebula. The remaining core, now a white dwarf, slowly cools over billions of years. A white dwarf is incredibly dense, packing about the mass of the Sun into a volume no bigger than Earth. A teaspoon of white dwarf material would weigh several tons. More massive stars have more dramatic deaths. A star with more than about 8 times the mass of the Sun will fuse heavier and heavier elements in its core, building up layers like an onion, hydrogen burning on the outside, then helium, then carbon, neon, oxygen, and finally, silicon. Each layer produces a different element through fusion. But when the core is converted to iron, fusion stops because fusing iron doesn't release energy. It absorbs it. With no outward pressure from fusion to balance gravity, the iron core collapses in a fraction of a second. The collapse happens so fast that the outer layers don't even have time to fall inward. When the core reaches the density of an atomic nucleus, it rebounds, and the resulting shock wave blows the rest of the star apart in a supernova explosion. For a few weeks, a supernova can outshine an entire galaxy of hundreds of billions of stars. The core that remains after a supernova is an extraordinarily dense object. If the original star was not too massive, the core becomes a neutron star, a ball of neutrons just 20 kilometers across, but containing more mass than the Sun. Neutron stars spin rapidly, sometimes hundreds of times per second, and they emit beams of radiation from their magnetic poles. If one of these beams sweeps past Earth, we see a pulsing signal, which is why rotating neutron stars are called pulsars. If the original star was massive enough, not even neutron pressure can halt the collapse. The core keeps falling inward until it becomes infinitely dense, a point of zero volume called a singularity, surrounded by a boundary called the event horizon, from which nothing, not even light, can escape. This is a stellar mass black hole, a gravitational monster born from the death of a supergiant star. Monsters in the dark. Black holes are among the strangest objects in the universe. They are regions of space where gravity is so strong that the normal rules of physics break down. Anything that crosses the event horizon is trapped forever, doomed to fall toward the singularity at the center. Despite their name, black holes can actually be incredibly bright. Not the black hole itself, of course, but the material falling into it. As gas spirals inward, it forms an accretion disk, a swirling vortex of superheated plasma that can reach temperatures of millions of degrees. This accretion disk radiates intense energy across the electromagnetic spectrum, from radio waves to X-rays. Some black holes also shoot jets of material perpendicular to the accretion disk at nearly the speed of light, creating cosmic searchlights that can extend for thousands of light years. Stellar mass black holes, the ones formed from collapsing stars, typically contain between 5 and 50 times the mass of the Sun. But there's another category of black holes that dwarfs these: supermassive black holes. These monsters lurk at the centers of most, perhaps all, large galaxies. They contain millions to billions of solar masses crammed into a region not much larger than our solar system. We now know that there's a supermassive black hole at the center of our own Milky Way galaxy. Called Sagittarius A star, it contains about 4 million times the mass of the Sun. We can't see it directly because it's hidden behind vast clouds of dust and stars. But we can observe stars orbiting around it and infer its presence from their motions. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, produced the first direct image of a supermassive black hole, the one at the center of galaxy M87. It appeared as a bright ring of light surrounding a dark shadow, exactly as Einstein's equations predicted over a century earlier. How did supermassive black holes form? This is one of the great unsolved mysteries in astronomy. They must have grown from smaller seeds, but even the most optimistic calculations struggle to explain how they could have reached billions of solar masses in the time available. Some might have formed from the direct collapse of massive gas clouds in the early universe. Others might have grown through mergers with other black holes. The answer probably involves both processes and others we haven't yet imagined. When two galaxies collide and merge, their central black holes eventually spiral together and coalesce. These mergers release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. In 2015, the LIGO detector made the first direct observation of gravitational waves from two stellar mass black holes merging over 1 billion light-years away. It was a momentous discovery, opening an entirely new way of observing the universe. Islands of stars. The Milky Way is our home galaxy, a vast spiral of several 100 billion stars spanning about 100,000 light-years across. Our solar system is located in one of the spiral arms, about 26,000 light-years from the galactic center. We're not at the center of anything. We're on the outskirts, in the galactic suburbs. When you look up at the night sky and see the Milky Way as a band of diffuse light, you're looking at the combined glow of billions of distant stars in our galaxy's disk. Each point of light is a sun, perhaps with its own system of planets. The scale is almost incomprehensible. If the sun were a grain of sand, the nearest star would be another grain of sand about 4 miles away. The entire galaxy would be a disk of sand about 100,000 miles across. Galaxies come in many shapes and sizes. Spiral galaxies like the Milky Way have flat, rotating disks with spiral arms where new stars are forming. Elliptical galaxies are more rounded, with older stars and little ongoing star formation. Irregular galaxies have chaotic shapes, often the result of gravitational interactions with other galaxies. Galaxies are not evenly distributed through space. They cluster together in groups and clusters, bound by gravity. Our local group contains the Milky Way, the Andromeda Galaxy, and several dozen smaller galaxies. The Andromeda Galaxy, about 2.5 million light-years away, is the most distant object visible to the naked eye. It's also heading toward us at about 100 kilometers per second. In about 4 billion years, the Milky Way and Andromeda will collide and eventually merge into a single giant elliptical galaxy. Galaxy clusters contain hundreds to thousands of galaxies spread across millions of light-years. The Virgo cluster, about 50 million light-years away, is the nearest large cluster and contains over 1,000 galaxies. Our local group is actually on the outskirts of a much larger structure called the Virgo supercluster. Beyond superclusters, the universe takes on a foam-like structure. Galaxies are arranged along walls and filaments surrounding vast, nearly empty voids. This cosmic web was shaped by gravity acting on tiny density fluctuations in the early universe, amplified over billions of years. The largest known structure is the Hercules Corona Borealis Great Wall, a string of galaxies stretching over 10 billion light-years across. The beginning of everything. How did the universe begin? This is perhaps the most profound question humans have ever asked, and remarkably, we have an answer, or at least the beginning of one. About 13.8 billion years ago, the universe began in an event called the Big Bang. This wasn't an explosion in space. It was an explosion of space itself. Time, space, matter, and energy all came into existence at that moment. Before the Big Bang, there was no before in any meaningful sense, because time itself hadn't started yet. In the first fraction of a second, the universe went through an incredibly hot, dense phase where the fundamental forces of nature separated from each other and the basic building blocks of matter came into existence. Quarks combined to form protons and neutrons. The universe was a seething plasma of particles and radiation, so hot and dense that light couldn't travel through it. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This was a pivotal moment because it made the universe transparent. Light could suddenly travel freely through space, and that light is still traveling today. We call it the cosmic microwave background radiation, and it fills all of space with a faint glow corresponding to a temperature of about 2.7 degrees above absolute zero. The cosmic microwave background is our baby picture of the universe. Tiny variations in its temperature, corresponding to slightly denser and less dense regions in the early universe, became the seeds from which all the galaxies, stars, and planets eventually grew. Gravity pulled matter together over hundreds of millions of years, forming the first stars and galaxies. The evidence for the Big Bang is overwhelming. The cosmic microwave background matches the predictions of Big Bang theory almost perfectly. The abundances of the lightest elements, hydrogen, helium, and lithium, match what we would expect to be produced in the first few minutes of the universe. And everywhere we look, distant galaxies are moving away from us, their light red-shifted by the expansion of space itself. But what happened in the very first instant? Before even the earliest phases we can reconstruct? What triggered the Big Bang? Why is there something rather than nothing? These questions remain unanswered, lying at the frontier of physics, and perhaps beyond the reach of science altogether. The dark universe. Here's a humbling fact. Everything we've talked about so far, all the stars and galaxies, all the planets and moons, all the gas and dust and black holes, accounts for only about 5% of the total mass energy of the universe. The rest is dark, invisible, mysterious. About 27% of the universe is dark matter. We can't see it because it doesn't interact with light. It doesn't emit, absorb, or reflect electromagnetic radiation of any kind. Yet we know it's there because of its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Galaxy clusters are bound together more tightly than visible matter can account for. The cosmic microwave background has patterns that require dark matter to explain. What is dark matter? We don't know. It might be an undiscovered particle, something that interacts through gravity and perhaps the weak nuclear force, but not through electromagnetism. Experiments deep underground are trying to detect dark matter particles directly, and particle accelerators are searching for them indirectly. So far, dark matter remains elusive. Even stranger is dark energy, which makes up about 68% of the universe. In 1998, astronomers measuring distant supernovae made a shocking discovery. The expansion of the universe is accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster over time. Something is pushing the universe apart, counteracting gravity on the largest scales. We call this something dark energy, but that's really just a name for our ignorance. It might be a property of space itself, a cosmological constant that Einstein first proposed and then abandoned. It might be evidence of new physics, something wrong with our understanding of gravity on cosmological scales. It might be something even weirder, like extra dimensions or a slowly changing field pervading all of space. The existence of dark energy changes our understanding of the universe's fate. In a universe dominated by matter, gravity would eventually slow the expansion, perhaps even reversing it in a big crunch. But in a universe dominated by dark energy, the expansion will continue forever, accelerating as it goes. Galaxies outside our local group will eventually recede faster than the speed of light, their light redshifted to infinity. In the far future, the observable universe will shrink to just our local group, then just our merged galaxy, then nothing but darkness as the last stars burn out. The far future. What does the future hold? If current theories are correct, the universe has a very long and mostly very boring future ahead of it. For the next few trillion years, stars will continue to form from gas and dust. But the raw materials are being used up. Eventually, no new stars will be born. The existing stars will burn out one by one, the smallest and coolest lasting longest. Red dwarf stars, those with less than half the mass of our sun, can burn for trillions of years, far longer than the current age of the universe. They'll be the last lights to go out. When all the stars are gone, the universe will be filled with stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down to stillness, black holes quietly growing in the darkness. Even these won't last forever. Over inconceivable timescales, protons might decay, causing white dwarfs and neutron stars to slowly evaporate. Black holes themselves will eventually evaporate through a process called Hawking radiation, though this will take times so long that numbers become meaningless. In the end, if the universe expands forever, it will become a cold, dark, empty void, slowly cooling toward absolute zero. Physicists call this the heat death of the universe, the maximum entropy state where nothing further can happen because there's no energy gradient to drive any process. It's not a bang or a crunch. It's just a slow fade into eternal nothingness. But this is so far in the future, trillions of years from now, that it shouldn't cause any existential dread. We have billions of years before our sun even begins to change. Plenty of time for life to spread through the galaxy and perhaps the universe. Plenty of time to find answers to questions we haven't even thought to ask yet. You are the universe looking at itself. We've traveled from the heart of our sun to the edge of the observable universe, from the first moments of time to the far future when the last lights go out. It's been a long journey, but there's one final thing I want you to understand. You are made of star stuff. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was created in a supernova explosion. The oxygen you're breathing right now was produced by nuclear fusion in stars that died before our solar system even existed. You are not separate from the universe. You are a part of it. You are a way for the cosmos to know itself. 4 billion years of evolution have shaped a brain capable of contemplating the very forces that created it. Atoms that spent billions of years drifting through space are now organized into a pattern that can wonder about its own origins. There's something almost miraculous about that, if you stop to think about it. The universe has looked at itself and asked why. We are small. Our planet is a tiny blue dot in an ocean of darkness, and our entire solar system is just one of hundreds of billions in our galaxy, which is itself just one of hundreds of billions of galaxies in the observable universe. But we are also the universe's way of understanding itself, the point at which matter has become complex enough to contemplate its own existence. So the next time you look up at the night sky, remember, you're not looking at something separate from yourself. You're looking at your own origins. You're looking at your cosmic family, the stars that made the atoms in your body. And in the silence between stars, the universe is looking back at you.